9-6. Today we are talking about growth and decay. This is also known as the annual compound interest formula. It has multiple purposes. If you're going to take either personal finance or QR next year, you will most likely see this formula in one of those classes. It is a very common formula to use in the finance world. Finance. Okay, let's talk about what these individual variables mean. A of t is your final total. And I also like to refer to it as the after. That's going to help you on some problems figure out what this number is. I get a pen too. Thin or thick?
Which one's thick?
This one. The A is the starting value. And I like to think of this as the before. So little a is before, big A is after. R stands for rate, and T stands for time. And then we have growth and decay. So if you look at the formula, you should notice the plus or minus here, 1 plus R or 1 minus R. That depends if you have growth or decay, and that is just based on the context. So as you can imagine, growth is 1 plus R and decay is 1 minus R. Let's try an actual problem. Number 1. Upon graduating college, Ashley took a job with a starting salary of $40,000. She gets a 6% raise each year. How much will she make after 7 years? So how I like to approach these problems, anytime I have an equation that has a bunch of variables in it, I like to make a list just like this list here and then fill in the values I have. This is especially useful in higher level math and in your science classes as well. You often have different formulas with different variables. This helped me keep my thoughts straight and figured out what I had and what I didn't have. So I'm going to make that little list over here. A of t, little a, R, and t. And we'll start filling this stuff in. I'll start with the 40,000. Before the word 40,000, or the number 40,000, it has the word starting. That's your hint that this is little a, your starting value. So now we know 40,000 is actually just little a. Next we have 6%. Percents are always going to be your rate. And we can't ever plug a percent straight into a formula. We have to use the decimal version of that percentage. So I'm going to show the work on the first one. How do we go about turning that into a decimal? 0.06. So we put a decimal if there already isn't one. So in this case there isn't one, it just goes at the end. And then it just moves 2 places to the left. So then a 0 will go there. So here's the new number, 0.06. This is what I'll be plugging into the actual equation. Thank you. So we'll have to do that every time. And then before I forget, this raise here, that's the dead giveaway what type of problem this is. What type of problem is this? Yeah. This is going to be a growth problem. There's usually a word or a phrase that will hint at which type it is, but they will never really come out and say it outside of a few different problems I can think of. And then the 7 years, of course, that refers to time, so that's going to be our t. T is 7. Meaning the one variable left, a of t, is the unknown. First thing I like to do is write out the general equation without anything plugged into it. A of t is equal to little a times 1, and since it's growth, this is a plus r problem, to the t power. And then we set up the equation. And I don't think I've ever read part A, write a function that models Ashley's pay. So all we're doing here is setting up the problem for part A, and that's it. We'll actually find our answer in part B. So plugging the numbers in, we don't know a of t. We know that little a is 40,000. Parenthesis 1 plus r is 0.06. Parenthesis, and then the exponent is t. So when it says write a function, this is what it's wanting. Just wants the setup of the problem. And then part B, find out how much she will make after 7 years. They want the answer. So I'm going to write this out. And when I do this, I'm going to go ahead and add inside the parentheses. A of t equals 40,000 times 1 plus 0.06 is just 1.06 to the 7th power. And that's obviously going to be a decimal, so I'm going to round. And this is money. I'll go ahead and put my dollar sign in there. Okay, calculator to get the answer. 40,000, that's a 4 with 4 zeros, times 1.06 to the 7th power. And we'll take it out to 2 decimal places. We'll go all the way out to the cents. That is $60,145.21. And that's our answer. Questions on number 1? And this is going to be our process for the next few problems. Number 2. A new car that sells for $18,000 depreciates. What do you think depreciates means? Decreases, yeah. It's as bad as it sounds. It goes down, it loses value. So this is going to be a decay problem. Which, if you think about it, when you buy a new car, it's not going to go up in value unless it's a classic. It's going to lose value over time. Depreciates 25% each year. We already know that 25% is the R. Write a function that models the value of the car. Find the value of the car after 4 years. That 4 is clearly going to be the t. I'm going to make my variable list here. We have big A, little a, r, and t. And for part A here, they just want us to build the equation. We already know that r is 25%, which we have to change into a decimal, 0.25. And then the t is 4 years, so 4. The one decision that trips a lot of students up is whether a given number is going to be big A or little a. I'll give you a couple ways to look at this. Number 1, we bought a car, brand new. It's currently $18,000. That is what it is right now. We know 4 years later, after, it's not going to be $18,000. So this is the starting value of the car, little a. And the wording here kind of gives it away because we're looking for the value after 4 years. That means we're looking for the after, big A. So we don't know the after yet. That's what we need to find. All right, let's build the equation. big A of t is equal to little a times 1. This is decay, so it's 1 minus r to the t value. Plug everything in. A of t equals, little a is 18,000, times 1 minus r is 0.25, to the 4th power. So this answers part A. Write the function. And then part B, we actually need to find the answer. A of t equals 18,000 times, I'll go ahead and subtract this. 1 minus 0.25 is 0.75 to the 4th power. And then I'll use my calculator and round. Once again, this is money, so I'm going to have a dollar sign here. $18,000 in parentheses 0.75 to the 4th power. Again, I'll go out 2 decimals. We have $5,695.31. So that is the new value of the car 4 years later. Questions on 2 before we move on to the backside? Number 3 is not going to be anything new. However, the context is an extremely important one. One of the big things that we use this equation for, if we talk about real-world application, is estimating population size, whether we're talking about humans or other species. So that's a pretty important way we use it. The population of a certain animal species decreases. That's about as obvious as it's going to get. That's clearly decay. At a rate of 3.5%. So that's our R. You have counted 80 of the animals in the habitat you are studying. How many animals will there be in 5 years? That's going to be T. And again, we're trying to find the number of animals after 5 years, so we can go ahead and determine that that 80 is a little a. This is before. Before, at the start of 5 years, we have 80. 5 years later, how many do we have after that? That's the question. I'll make the list. Big A, little a, R, and T. Little a is 80. R is 3.5%, which we need to change to a decimal. And we already have a decimal in that number, so from that decimal, move 2 to the left. 0.035. And then T is 5. Meaning, once again, big A, we don't know. We want to know the after. Setting up the equation, we have A of T equals little a times 1. Again, this is decay, so minus R to the T. Filling in, we have big A of T equals little a is 80 times 1 minus R is 0.035. And then the exponent T is 5. This is our function. And then B, solve it to estimate the population in 5 years. A of T equals 80 times. If we subtract here, that is 0.965 to the 5th. And then we use our calculator and round. $80 times 0.965 to the 5th. And this time I'm estimating animals, living beings, so I'm not going to give a decimal. I will round that to a whole number. 66.9, that does round up to 67 animals.
After 66. You can't have 69.9% of an animal, so I think you should round down.
We're estimating population. We're not trying to fit these animals into a carrier.
66.
I see what you mean.
You're not going to round up a person.
We'll discuss this later, but I see what you mean.
Okay, I'm not changing my answer.
Okay. Number 4. Ashley is back again with an initial salary of $40,000. And let's come back here real quick. What does the word initial mean? Starting. It's kind of important information to understand to be able to correctly label. So, since we know that is the starting salary, we know that this is A. And now makes $60,000. So she started with 40, and she now makes 60 before and after. The now 60, this is big A of T. She gets a 6% raise each year. That's going to be the R. How long has she worked at this job? That's what we don't know. T is what we're solving for here. I'll make the list. Big A, little a, R, and T. So we know big A is 60,000. Little a is 40,000. R is 6%, which we need to make into a decimal, 0.06. And T is unknown. That's what we're trying to find out. This is where the list can be really helpful. Trying to figure out what you do and don't know. All right, let's set up the function. A of T is equal to, and I forgot to point out that this is growth. She's getting a raise. So this is a growth problem. A times 1 plus R to the T. And then we fill in. This time we do know A of T, it's 60,000. Equals little a is 40,000. Times 1 plus R is 0.06. To the T power. T is unknown. So this is the function to solve. And if you can't tell by looking at it or by the amount of space underneath part B, we're not just going to be able to use our calculator and then move on. We're going to have to do some work. So I'm going to write that down again. We have 60,000 equals 40,000. I'll go ahead and combine the number in parentheses. 1.06 to the T power. And we need to solve this. Any suggestions on how to start?
Like file PEMDAS. Because I'm thinking like you try to get the T by itself, right?
Mm-hmm. We're trying to get the T by itself, which means we need to get this by itself. Yes.
So you would
Not subtract.
divide.
So remember, when these are smashed together like this, that's multiplication. So the only way to move would be division. So that's how we're going to have to handle this. Divide by 40,000 on both sides. And I'm going to do a lot here. So I'm going to write my steps out as I go. Might help later to look back on. Divide by 40,000. Now that is going to be a very nice number. A 6 with 4 zeros divided by a 4 with 4 zeros. did that wrong. Hold up. I did 3 zeros. Let me fix that. Okay. 1.5. 1.5 is equal to, you can drop the parentheses, 1.06 to the t power. This next step is optional, but I'm sure most of you would find benefit from it. This is backwards from what we're used to looking at, so I am going to flip the sides of the equation. So I'm going to put the left side on the right side and the right side on the left side. 1.06 to the t equals 1.5. So step 2, flip equation, which in this unit is a very helpful strategy. Step 3. Classify. What type of problem do I have here? What type of equation? I'll give you a hint, it's not a log. So what is it? Exponential. Exponential on the left, number on the right. Exponential equals number. Again, you got to practice the problem recognition. That's going to be a huge topic on this test. Exponential equals number. There are 2 ways to solve an exponential. Option 1, get the same base. Anyone want to give that a shot? Didn't think so. Option 2, what is it? What'd you say? Turn it into a log. We switch the form. Switch form and solve. So, we are currently in exponential form. And we're going to put it in log form. When you write a log, the first thing you write is the word log. Base stays base. My base is 1.06. The other 2 switch a root. So 1.5 over here and t on the right side. Now we are basically done. I'm just going to get my answer. And I'm going to flip this around. So we have t equals log base 1.06 of 1.5. And then we need to be able to put that in the calculator. Remember, it's where I draw the line here to see how to divide it up. Change a base formula, log of 1.5 on top, log of 1.06 on the bottom. That's what I'll type into the calculator. And then I'll round. So we have log of 1.5 divided by log of 1.06. And years, we'll just go to the whole number. 6.9, that is 7 years.
I got the same answer, but I had to do a lot less work.
You can show me your method later.
Oh, it's so cheesed. You're going to be like, well, that's not the math way to do it.
Okay. Any questions on 4 before we do 5 and 6? Number 5, or I'll show you the directions first. Decide if each function is an example of exponential growth or exponential decay. If you know what you're looking for, you can eyeball this, but I'll show you the process to get said answer. So what we need to do here is find r. You find r, you can answer the question. Number 5, y equals 12 times 0.95 to the x power. Now this guy here is like this here, where we have the already condensed number. We don't have the original, so if we had this, we could tell automatically, but that's not what we have. So let's figure out what that was initially. So in the parentheses, we know that this is 1 plus r. So I'm going to set up a little equation. 1 plus r is equal to 0.95. And then we find r. Minus 1, minus 1. R equals, if you subtract this, negative 0.05. We got a negative number, so what do we think? Growth or decay? Decay it is. If your rate is going down, you are decreasing. And number 6, I'm going to do the exact same thing. Number in parentheses, that's the 1 plus r. So that means we have 1 plus r equals 1.35. And I'm sure most of you could eyeball this one. Minus 1, minus 1. R is 0.35, which is a positive number. So that means we have growth. Questions on 5 or 6?